Good day to you all. We continue with our topic on tower and tower internals, and we will be talking today on the design of packed towers. So far what we have covered regarding tower and tower internals are the tray towers, the different type of tray towers, and then we have come to the packed tower design right now. To start with, we need to know that what are the basic considerations for choosing between the packed and the tray towers. So, we have two options of vapor liquid contacting, that is what we have been focusing on, and we need to find out what exactly are the advantages and the limitations of each type. Here we have a few considerations listed. If we look at the pressure drop per theoretical stage of contact for the same vapor liquid load, we normally find that the pressure drop per theoretical stage of contact is lower for packed compared to the tray towers. The packed towers offered a lower pressure drop per theoretical stage. Then if we look at capacity, well, the same thing follows from the previous one itself. That means, if we have the pressure drop as a limitation for my tower, the capacity would be higher in case of packed. So, in case of packed, the capacity will be higher. Regarding energy consumption, well, that is a very interesting part, because it is energy consumption will be given in this particular case volumetric flow rate divided by delta P. If your delta P is lower in case of packed tower, naturally the energy consumption would be lower in case of packed tower. So, I can straight away write that packed tower will have a lower energy consumption. It is more difficult to talk about the maintenance and inspection facilities. Maintenance required for the tray towers and packed towers, it depends a lot on the type of service that it is providing. For example, tray towers, the tower trays, they have a tendency to fall in case of pressure surges. So, they are required to be periodically repaired, inspected and all, and maintained certainly. In the same thing, like the pressure surge in case of packed tower will normally disrupt the packing, and once disrupted, it has to be repacked, at least the top part of it. So, I will not basically decide between the packed and the tray tower, and I will say they are more or less equivalent. Regarding the material of construction, well, distinctly we can say that if we are going to handle something corrosive, since your tray towers are always metal towers, it is possible for you to have only the shell to be of a noble metal, not noble metal, of a higher metallurgy, and you can have your packing which is fairly inert. It could be graphite or something which is basically non-corroded. So, you have some advantage in case of packed tower, but because the packed tower can have non-metallic packings. If we talk about the liquid hold up on a tray, typically the depth will be of the order of 2 inches or 50 millimeters, whereas it is expected to be lower in case of packed towers. When we compared this, we compared the hold up on a single stage, equivalent single stage in case of a packed tower, and compare it with the say approximately a tray which has got very close to efficiency 1. So, your packed tower has a typically lower hold up. Regarding change in feed composition, here the tray towers win, because if you are really to provide multiple feed points, it is much more easy to do during the design and the construction in case of tray towers, whereas it is relatively more expensive and it is difficult to do it in case of tray towers, because for every feed section in the vapor liquid contacting tower, you have to have a distributor and similar details. which is not so in case of tray towers. Tray towers are better with respect to this point. So, I can straight away write tray towers are better equipped, because we can have alternate feed locations. Regarding the foaming and emulsional formation tendency, it is obvious. If you look at the construction of the tower, the foam breaks in the clear space. So, almost the entire tower section will be available for breaking of the foam. So, quite naturally, for this purpose I can always say tray towers are better. If you look at the tower diameter, here also it is very difficult to say. The tower diameter will basically depend on the approach to flooding. For the same approach to flooding, it depends on what type of packing you have. Well, you can say the tower diameter requirement you cannot straight away say. In some cases it will be, I mean, either could be better. Regarding temperature cycles, the trays win. The trays are metallic trays, and almost all components on the tray, they are metallic and they have a similar coefficient of expansion. Whereas, if you have a packed tower where the packing material expansion coefficient and the shell material expansion coefficients are usually different, during temperature cycles there will be contraction or expansion of these two, which will create, and usually what happens is, if you are having packing of a brittle material, the packings start crumbling. This is particularly true if you are using some brittle material like ceramics as packing. Sometimes even the carbon rings also, they crumble down. So, temperature cycles are much better handled by tray towers, and the reason is obvious. Regarding presence of solid, tray towers win. The tray towers win because of a very simple reason. Because, for example, if I have a tray tower which is fitted with bubble caps, I can have a long riser and a fairly large clearance below the skirt of the bubble cap. This is something which we have already discussed earlier while discussing the bubble caps on the trays, and we can still have a little bit of solid deposition on the tray deck, whereas if there is some solid deposition on the packing material, it will restrict the flow of the gas and the liquid both. So, that way to some extent, I mean, in no vapor liquid contacting you expect that there should be a large amount of solid, but even if it is there, due to some unavoidable reasons, your tray towers will be performing better. Regarding heat removal capacity, yes, if you are talking about the heat removal capacity, it is possible for you to have some sort of heat removal arrangement like embedded tubes and embedded heat transfer tubes and all. In case of tray towers, in fact, if you are talking about the divided wall column or something, it is possible to have it in case of tray towers, but you cannot have such facility in case in packed towers. So, if you look at heat removal capacity, I will say that tray towers are better, rather they have the advantage. Regarding liquid flow rate, if you are talking about the liquid flow rate, the ideal liquid flow rate for a packed tower is just weighting of the surface of the packing. If you have a very thin layer on the packing surface, what happens is your diffusion length inside the liquid is less. You will have sufficient amount of turbulence on the liquid film that falls and flows on the packing surface also. In case of trays, if you are going to have a large amount of liquid flow rate, yes, you have a large gradient. But in case of packed tower, there is a limitation. The limitation is, it is not due to the packing. The limitation is, in case of packed tower, it is of utmost importance to avoid channeling, and the channeling is better avoided by having a uniform distribution of the liquid over the packing itself. Normally, whatever type of distributor you have in case of packings, they have a limited range over which they function well. So, I will say this is limited for packed towers due to, it is due to what? It is basically due to the distributor efficiency. That means, if I have my distributor to distribute the liquid evenly, there will be a fairly narrow range of liquid flow rate, and that limits the operating range of liquid flow for your packed towers, whereas it is not so in case of tray towers. In case of tray towers, well, if you really have very low rate, possibly your height above the wear, the outlet wear would be small, and if it falls below 6 millimeters, you do not have good distribution and a uniform flow. And at the same time, if you have a very high liquid flow rate, what happens is, if the gradient of liquid across the tray is large, and you may have channeling wherever you have lower depth of liquid. That we have already discussed in case of tray towers. Now, we talk about the turn down. Before we talk about turn down, perhaps we should answer this question: what is turn down ratio? The turn down ratio is basically the design capacity divided by the minimum operating capacity. So, one thing is true, the turn down ratio, if I define this way, the turn down ratio is going to be above 1, true. That means, had the turn down ratio, we can have a lower operating capacity. That means, if I have a turn down ratio of say x, which is say 1.5, that means, if I have my design capacity of 1.5, I can still go up to a capacity of 1. That means, higher the turn down ratio, lower the feasible minimum operating capacity. Quite naturally, in case of turn down, you will naturally find that you have a very limited range of distributor operation in case of packed tower. So, this is definitely higher for trays. You will notice one thing, the turn down ratio, it is not only for the trays, but it is also true for any equipment for that. Now, there is a question here. For example, you will also notice that the turn down ratio does not necessarily depend on the major component of your equipment. For example, the turn down is limited by the distributor which is fitted to your packings. So, it is not the packing which decides it, it is a distributor fitted on the packing, liquid distributor, which we shall decide the turn down. Now, regarding flexibility in operation, well, if you are asking me, I will say that the flexibility in operation is fairly okay, in the sense particularly if I have a higher turn down ratio, my flexibility would be more over, because I can operate over a large capacity range without much loss in efficiency of contacting. So, I will say this is more with the same logic, more for the tray columns. I believe with this we have discussed the different considerations for choosing between the trays and the packing, and if you are facing a problem, design problem, you can use these points in order to find out what exactly is the best option that you can have for your contacting. Before we go into the design of the packed towers, let us look at typical problems, the design problems as are faced. Here we have a design problem which simply says that minimum 95% of the sulfur dioxide which is present in the air stream, I could have put it like this. This belongs to the air stream, which is having 8% sulfur dioxide in it, and the flow rate is 500 kg per hour at a 20 degree centigrade temperature, and this is to be removed by contacting with water in a packed tower, packed bed absorber. And you are asked to do a preliminary design for the absorption column operating close to atmospheric pressure. That means, one thing is true, that possibly there is a low pressure blower which is going to supply this particular SO2 laden air to the absorption column, and you will have a counter current contacting over there. You will send obviously the air from the bottom, and the liquid and the water will be coming from the top. This is basically a typical absorption problem. So, if we know that this is a typical absorption problem, and we already have done the lecture and the notes on absorption we already have, it is possible for us to find out two things. Number one, the number of theoretical stages and the diameter. Once we have these, the next thing that we are required to find out is, for this system, what is the height equivalent to a theoretical plate. Now, when I multiply this A and this B item, what do I get? We get the active bed height which is required for this particular contacting. So, with this we understand that we are going to require some active bed height of a particular diameter, and we know the number of theoretical stages that is required for this contacting as well. And the procedure for finding this we already have covered in your lectures in absorption. This is the diameter, this is the diagram which you have already seen earlier, where you have a typical demonstration packed tower and what are its components. Quite naturally, the gas is exiting from the top, and the liquid is distributed from the top itself through the liquid inlet, and it comes out from the bottom, and here it, as it shows, you have a redistributor. We will see how to arrive at the basic dimensions and the features of each of these. There are two packed sections. One section is packed with a structured packing, the other is with random packing, which is damped. Perfect. Let us look at the other features now. You have been supplied with a design problem. What are the inputs? These are the inlet flow rates of gas and liquid. Yes, you already have found out how to find out the minimum amount of liquid required, and based on that, based on the minimum liquid, you have assumed about 1.5 tons of that liquid rate, and possibly definitely by this time, when you have come to the design of the bed itself, you know what are the inlet flow rates. You know obviously the composition of the inlet gas and the liquid. You know the desired change in concentration of the transferred component, and or the minimum, which is certainly related to the minimum target of recovery of the components. Here in this specific problem, you have a requirement of minimum 95% recovery of the sulfur dioxide, that means removal in that case. You know the operating pressure and the maximum permissible pressure drop across the column. We are going to have a very small pressure drop across the column itself, because we know that ultimately the pressure supplied is not very large, and we cannot afford to have a higher pressure drop. The chosen solvent or the inert gas, it is not a stripper. So, in case of the absorber that you have been given, the solvent is just a stream of water. So, this is also known. The phase properties, I am not going into the details of these, but these are all known as well. As a design output, you got to first choose the deliverable, that means you have to tell the packing material type and size. Naturally, the size is usually a nominal, the type is there could be various shapes of the packing material, which we will just see after this. The active bed height, yes, definitely we have to verify that whatever we are delivering now is in a position to provide the desired active bed height, which we have seen in the last slide. The bed diameter, certainly so. We have to provide the details of the top liquid distributor, and if we really require any redistribution or any side stream draw off, which is not required in this specific design problem, if it is required, we have to provide the basic design features of these as well. The bed has to be supported. So, naturally we have to talk about, and we must know about the bed support and the top restraint details. Packed beds often require a top restraint, so that the top layer of the packing does not get blown off during mild pressure surges even. You have to provide definitely the tower shell details, the internal fitting that we have been talking about now, but you are also to provide the location, the elevation of the manholes, nozzles, and the support details. The support details, obviously, the first thing that you have to provide is the elevation of the bottom of your column, and that depends on the NPSH requirement of the pump that is supposed to pump out the liquid from the bottom of this particular tower. This also we have discussed earlier. Now, let us look at the desirable characteristics of the packings. The packing has to be supported. So, the lighter the packing, the better it is. So, lower weight per unit volume, when I say unit volume, it means the packing volume, that means the packed bed volume. The same thing is true in case of larger surface area per unit volume, which is basically the meter square surface area per meter cube of the bed volume. The larger it is, more will be the surface over which the liquid can spread and can contact with the vapor which passes by. You must remember one thing, whenever you are talking about the pressure drop in case of similar this type of beds of vapor liquid flow, the pressure that is lost by the gas is primarily at the vapor liquid interface. You require definitely a large void volume, because a large void volume of your packing, the type of you choose, if you have that, your pressure drop is definitely going to be much less. The void volume can vary anything between 60, 65, even less than that, 58, maybe 60 in case of ceramic packings or stoneware packings, to roughly about 95% voided in case of metal packings. Low liquid hold up. Yes, low liquid hold up is basically something we desire. We already have said that we will always prefer a thin liquid film wetting the surface of the packing. So, naturally, if you have a thin film, you would have a low liquid hold up. So, they are complementary qualities. Inexpensive, it is too obvious to say that why we require something to be inexpensive, because the material that is required in order to have as packing, usually the volume is large, the quantity is large. So, it should not be too expensive. The packing has to survive its own weight, the tower packing. So, naturally, it must have a reasonable amount of mechanical strength. It should not get crushed by its own weight. Not only that, there is another thing which requires the mechanical strength to be high, that is, when you fill a tower, what you have to do is there are two ways you can do it. You can have a tower which is filled with liquid. If you are sending random packings, you will be dropping the packings after, if this is water or some liquid, possibly it will be water in most of the cases, then you will be dropping the packings, and the packings would come and settle down at the bottom, and gradually there will be a bed build up like this. The other way is to have a chute. That is also quite common. So, you have a bottom support here, here also you have a bottom support, and you have a funnel to which a chute is here. Possibly there will be someone who will be hanging here almost with a ladder, and he will be directing the chute in this position, and this position, and this position, and this position, and he will be gradually building this up. So, both are required, and particularly you require a reasonable mechanical strength, because if your packings are dropped from the top, it should not break. So that your impact is less, you usually fill it up with water and let it settle down at a slower rate. It is too obvious to ask for this. Your packing must be inert towards the components that are involved here, and it should not rust also. We have been introduced to the structure and the random packing both. The random packings typically they have different characteristics, advantage, disadvantage, and there are different types. Here L by D of this cylinder is nearly 1. This is a Raschig ring. There is a partition in between. This is a Lessing ring. You have a cross partition here. So, this is called a partition ring. These two are saddles. These are called, they have the saddle shape, so they are called barrel saddles. This is called a telluride packing. And here what you have is a slightly more complicated structure, usually made of metal. This is called a Paul ring. There will be nominal sizes of these. Typical sizes could be 1 inch, 1.5 inch, it could be even lower. And there is something which is very important. If you look at the characteristics, you will find that the size needs to be compatible with the tower diameter. If you have too large a size of packing, there will be more of channeling. The tower diameter has to be minimum 10 times larger than the packing, or rather in other words, my packing size should be 1/10 or even lower. Next, regarding the structured packing, what we can say, the structured packings are proprietary. In fact, many of these designs are also proprietary. That means, many of these random packings are also proprietary, but Raschig rings and Lessing rings and partition rings you can make yourself. They usually have L by D is equal to close to 1, and you can make yourself, or you can source it from somewhere. If you have to have barrel saddles, Paul rings and tellurides, you have to buy it from the standard vendors who are available. Now, let us look at the structured packings, what exactly they are. Structured packings actually they contain passages and they come in blocks. So, if I have a block of structured packing which is going to look like this somehow, you will have corrugated sheets. You have corrugated sheets which are like this. They are vertical corrugated sheets, and these blocks can be placed side by side, they can be placed one above the other also. So, one good thing about if you are placing these blocks one above the other is you can almost align one block outlet with the inlet of the block which is above that. That means, there is less amount of deviation in the flow direction of the fluid, I mean basically the liquid and the gas both, as it flows from one block to the other block element. All these usually are tied with a ribbon, a metal ribbon made in this particular shape, and these shapes are placed one above other, and while you place these you have to be very careful that you try to have as much of alignment as possible. These are proprietary, these are much more expensive, but obviously since all the holes are aligned to the extent possible, the pressure drop in these are much less. Number one, for the same bed height, the pressure drop in the structured packing is much lower as compared to the dumped or the random packing. They are expensive, and it is obvious that it will be more prone to maldistribution if there be a maldistribution of liquid initially. Suppose you have more liquid falling in here and you have less liquid falling in here, obviously the same thing will have a tendency to continue. That means, in case of structured packing, it is very important that you have as uniform a distribution of liquid at the top as possible. Now, I already have answered the question which I had put at the bottom, that is, why do structured packings incur lower pressure drop? Because of the alignment of the openings. here we have some limitations. When you are going to design a tower, there are certain limitations, practical limitations you got to honor. There is a minimum tower diameter and the maximum liquid loading for random packings. The random pack, and it depends on the nominal size of the random packing itself. The nominal packings are typically 3/4 inch, 1 inch, 1.5 inch, 2 inch, 3.5 inch. So, these are the typical sizes. And quite naturally, we have to, if this be the size, the minimum column diameter has to be at least 10 times that. So, typical industry standards which are used are given here. Now, there is something which is also quite important, the maximum liquid loading. The maximum liquid loading would depend on what? If I have a particular size of packing, and if I want to push too much of liquid through it, it won't simply flow through the opening that it provides. The pressure drop would be large. So, quite naturally, if I have to provide a large amount of flow rate of liquid in meter cube per hour per meter square of tower area, and if it is large enough, I have to go for a larger nominal size of packing. The minimum D tower by D packing, I already have told you, is basically around 10. Some people say that it is around 12. Now, you could also use a smaller size packing, because a smaller size packing usually will be having a higher specific area. That means, the specific area means meter square of surface area per meter cube of the bed. But a smaller size packing will definitely have a problem of, will be offering you a higher pressure drop. So, it is not always desirable to go for the smallest size. The pressure drop could become a limitation. There is something which is very important in case of weighting rate. That means, in case of packed bed, we already have said often the rate of liquid flow is guided by the distributor design. The range in which the distributor can distribute fairly uniformly is the range of operation of your packed bed. Now, there is something else also. For example, when you are choosing a particular packing, there is a minimum weighting rate. That means, if I do not supply a packed bed with the sufficient amount of liquid flow, the entire bed surface will not get irrigated properly. Some of it will run dry. So, that is a loss. So, quite naturally, if you are deciding on a bed, your liquid flow rate has to be reasonably above the minimum weighting rate. How will you define a minimum weighting rate? We will see later, but obviously, it is something like this. It is basically meter cube per hour per meter square of the tower area again. This is a very important characteristics of the packing that you have. The different types of packings are here, the different types of random packings are here: Rashid ring, Burl saddle, Paul ring, metal interlocks, IMTP, North pack, high pack, and all these are proprietary. These ones are all proprietary ones, and these are all random packings. You have structured packings also, which are obviously proprietary, and here is a list of structured proprietary packings which is here. If you look at the material of construction, you see that the material could be ceramic. In some cases, you can have Rashid rings of ceramic, you can have Rashid rings of aluminum also. Similarly, it is also possible to have high pack, which could be a metallic packing, it could be a plastic packing also. Now, there is a nominal size which is given here. The void fraction is here. You will notice one thing very interestingly, that whenever you have ceramic, you need to have a reasonable amount of strength. You must have a thick wall. So, that limits your maximum amount of free space, which is epsilon. So, you have a 0.64 here, whereas if you look at any metal packing, it will be 0.94, 0.95, 0.96, 0.97 of this order. In fact, it has gone up to 0.98 in case of metal interlocks, so IMTP. The specific area of the packing is definitely in meter square per meter cube of bed. So, you see here how it varies, and you will see one big difference compared to this. In general, these are higher. That means structured packings normally they will offer a little bit higher contacting area or specific surface area. Now, here is one thing which is very, very important. The pressure drop in a packing or a packed bed is related to the characteristics of the packing. This Fp is a factor which you will be requiring later on in order to compute or estimate the pressure drop in your packing, which you have to, whenever you are designing, there must be a maximum limit of pressure drop in your bed. So, for that calculation you require the packing factor of Fp to be decided. Here this basically this document has been taken from Giancopoulos' book, and here there is one more thing which is quite important. How important, or rather how much it facilitates the mass transfer operations like the during vapor liquid contacting. In relative term it is given here. See, if it is say for 1.5 inch Rashig ring, if it is 1, in a comparative scale you can see these, and you will definitely find here that it is much higher as compared to the rest given here. You will also understand one thing very clearly, the smaller the size, like if you go for half inch Rashig rings, the relative mass transfer coefficient is 1.5 with respect to the same thing with 1.5 inch size. So, smaller the size, usually your mass transfer coefficient will be higher in a relative scale. Now, you need to know about the other design details. The liquid distributor in case of packed bed is very important. We talked about the different types of distributors. The spray nozzle header is very, very simple. Basically, what you have is, if you have a tower in which you have to spray, you definitely will be having this type of branches coming from a liquid entry distributor, and you will have your sprays located here. We will not go into the design details of this, but one thing we understand, that we would like to design such that you get fairly well amount of spray distribution here, and one thing is very, very important, your spray nozzles usually are proprietary. And definitely the angle of spray is an important point. What else? The operating flow rate range. And particularly when you are talking about the liquid distributor, you will understand, or you must appreciate, or you definitely keep in mind one thing. In a packed tower, usually the liquid will have a tendency to go towards the wall. That means the channeling normally will be happening close to the wall. I will leave it to you to think that why during channeling in most of the liquid field, most of the liquid will have a tendency to go towards the wall. That means there will be a higher flow of liquid close to the wall. Why it is so? Now, what I do is, you have the other type of distributors, which are the trough distributors. What is a trough distributor? The trough distributor is nothing. It is normally used in case of very large, reasonably large towers. You have a trough which looks something like this. I will just draw part of it. And here what happens is, you have liquid here, you have liquid here, and liquid falls through these troughs. So, what you have is, you have a trough in these locations, which is fed by a header itself, and it overflows from the trough. You can have pipe orifice headers which are very similar to this. Here what you have, instead of a spray nozzle being fitted to that particular header, you will be having orifices. Normally, if you have an orifice, what you will find is something like this usually. If I look at the pipe which is having an orifice, and this is my vertical line. Typically, you will have one hole here, one hole here. That means, and this angle is around 45 degrees, 45 degrees. So, what I would like to say is, if you have an arrangement of pipe orifice distributed, it will be like this, but at the same time you will find they are not aligned in the same line. Possibly one will be here, the second one will be here, they are offset. Now, you have a pan type of riser, pan type with a riser tube. This is something which we have discussed earlier, and this is the simplest type of distributor which you use, and what you have here is a pan deck. Basically, it's your this is your deck with liquid downcomer. That means, on the deck you will have a liquid, and the liquid will flow through these. So, this is the same thing here. That means, you have here a baffle plate, basically it is a flash baffle, on which you are having a distributor feed line, typical dimensions given here, either I mean these are all in millimeters. So, the liquid would fall, it will get distributed here, it will fall here, it will get distributed here, there will be a level of liquid, there will be a level of liquid, and the liquid would fall from these. Here only two downcomers or liquid downcomers have been shown. In order that the vapor which is coming below that, it goes up, there has to be a vaporizer. The vaporizer typically could be 100 millimeters, and it normally will be having a about 450 millimeter height. Typical depth of liquid here could be around 220 millimeters or something like this, 220 millimeters, 225 millimeters, and the variation in liquid height on this particular arrangement could be by about, say, the liquid height may vary typically 6 inches, that means 150 mm, depending on the liquid load here. The different technical details, the points are given here, so that you can read yourself. I do not think that I need to read it out for you, but there is something which is very important here. This deck must have weep holes. You have to have some arrangement for draining it when it is not in operation. The weep holes could be a good number. We have talked about providing weep holes on the decks earlier also in one of our tower internal classes. Based on that standard, you can provide weep holes of 3 to 5 millimeter size, typically 3 millimeters. How many to provide, you can find it out based on the weeping time that you decide for here. The pressure drop here, you definitely have to find out that what is the allowable pressure drop here. It is given here that the typical pressure drop could be about 170 to 350 millimeter water column, and the discharge coefficient is 0.6, and based on that you will be designing these. What is the diameter required? You will understand one more thing, that is, whenever you are talking about the liquid distribution within the 5 to 10% of the D, that means if this be your tower diameter, and this zone should be getting below 10% of the liquid, because if you put more amount of liquid here, it will have a higher tendency of channeling, and it will go and stick to your wall and fall down the wall itself. And one thing is repeated here, structured packings are more prone to initial maldistribution, because once it enters a particular set of partition of the corrugation or the corrugation, it moves down, and if it is, and the maldistribution does not get corrected automatically. To some extent, there is a chance of correction of the same in case of random packings. I think I will stop here with this and continue in the next class. Thank you.